number 27 right now. Okay, gravel's being dumped from a conveyor belt at a rate of 30 cubic feet per minute, and its coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. How fast is the height of the pile increasing when the pile is 10 feet high? Okay, so let's just picture what's happening. We're building a pile of sand, okay, and it's sort of forming a cone, and as my cone gets bigger, the diameter gets bigger, and the height gets bigger, and the coarseness is such that as the diameter gets bigger, the height's getting bigger, and they're both going to kind of stay the same length. I'm being asked to find dH/dt. So if I call the height of the cone h, I'm being asked to find dH/dt. This is what I'm looking for. And I can write a formula that relates the diameter, and I'm given information about the diameter. Okay, so I will leave it at that. And then we're told dV dt is 30 cubic feet per minute. Okay, so this is the rate that I'm given, and the dH/dt is the rate that I'm looking for. And then there's also this other variable d, the diameter. So once I read the formula or the problem and I figure out what I'm looking for and I figure out what I've been given information about, I try to come up with a formula that relates the two. So in this case, the formula is going to be the volume of a cone. And the volume of a cone is 1/3 of the volume of a cylinder of that same height and radius. Okay, so a cylinder is a circle with some height. Alright, so the area of a circle is pi r squared. That's where the r is the pi r squared is coming from. And then the height is giving you the volume. If you make that into a cone, you shave away 2/3 of that cylinder, and you're left with 1/3. Okay, so the volume of a cone is 1/3 of a cylinder that would have that same radius and height. Since they gave me information about the diameter, I probably want at the moment to rewrite that in terms of diameter. So radius is diameter divided by 2. And then for this particular cone, I mean, this certainly isn't true for all cones, but this particular cone, the diameter and the height keep changing so that they stay the same amount. So I can replace D with H. And so now I only have H and E in my formula. That up, I get pi h cubed over 12. Right? H squared times h is where I got the h cubed. Pi is in the numerator, but the 2 is being squared,
Yeah.
so 2 squared is 4, and 4 times 3 is where I got 12. Alright, so as time changes, the amount of sand changes, so the volume changes and the height changes. The diameter changes too, but I've already built that into the formula. So V is a function of time, H is a function of time. So my implicit differentiation will look like dV dt, rate of change of volume with respect to time, is equal to 3 pi h squared over 12 times dH dt, because h is a function of time plugged inside of that cube. So this is the derivative of the outside, and then this is multiplying by the derivative of the inside. So let's see, we have 30. I'm leaving the units off right now just because it makes the equation look messier, but it is good advice to double check your units in the end, because if units don't work out, you probably left out some variable or something, okay? The units can often tell you if you're doing the problem right. But if I start to write the units with everything I know, it makes the equations look messy. Okay, so we were told that this was 30. I'm looking for this, and then we want the rate of change when the height is specifically 10 feet. So now that I've taken the implicit derivative, I can go ahead and plug my 10 in. I didn't want to do that until after I did the implicit differentiation though. So I get 120 divided by 100 pi